robot runs on ROS2, each capability is its own node, communicating over topics. The camera feeds 3 parallel perception nodes: line detection, traffic lights, and YOLO sign recognition. A line follower converts that into wheel speeds, and a behavior controller overrides them when a sign demands it. Messages are just floats, pulls, and strings, simple by design. We tune live with ROS2 param set and swap launch files depending on what we're testing.
The robot recognizes 6 traffic signals: stop, yield, roadwork, turn left, turn right, and go straight. We build the dataset in RAWflow, capturing images of each sign under different lighting and angles, then labeling them with bounding boxes. RAWflow handled the train validation split and let us play augmentation like brightness, cutout, and blur, so the model generalized to the real track instead of memorizing perfect shots. We train a YOLO V8 object detection model on that dataset and then export it to a tensor engine, which is what makes inference fast enough to run on the Jetson in real time. On the robot, the sign node runs that model on every frame, ignoring boxes that are too small or low confidence. Picks the largest detection and only confirms a sign after it appears across several consecutive frames, so a single noisy frame never triggers an action.
Here is an example on the bigger track. We can see how the robot is turning left following the lines, and on the right side we can see how the robot is slowing down and then turning left when seeing the corresponding signs. For the line follower, we were doing classical vision. We basically convert a frame to grayscale, threshold it to isolate the dark line, and only look at a region of interest near the front of the robot. We use an adaptive threshold so changing light and floor color don't break detection. From the thresholded image, we find contours, keep the largest view, and pick the one closest to the center of the frame. That's our line. Fitting a rotated rectangle to it gives us 2 numbers: how fast the line is shifted left or right and how tilted it is. Those feed a PD controller. The shift keeps us centered, and the angle terms lets us anticipate curves before we drift. The output is a turn state, and on sharp turns we automatically slow down so the camera keeps the line in view.
All of these inputs are arbitrated by a behavior state machine with a strict priority. The traffic light comes first. Red means full stop, yellow slows us to 40%, green or none means go. And it only switches a state after a few stable frames, so a flicker never stops us. If no light overrides us, signs take over. When a turn or straight sign is confirmed, the robot keeps following the line normally. Then after a fixed 2-second delay, it executes a hard-coded maneuver. A short straight approach, then a timed pivot left or right, or a timed straight crossing, before handing control back to the line follower. Stop, yield, and roadwork each have their own states too, and at the bottom of the priority list, when nothing else is active, the robot simply follows the line.
Watch the robot follow the line and stop at a red light, resume on green, and take its turns at each intersection. Our biggest early problem was the camera. Assuming in a sensor mode was cropping our file of view, so the robot lost the line zone curve, switching to a full file of view mode fixed it. We also rebuilt how turns are triggered, moving from a faulty intersection detector to a simple reliable after the sign scene. The result is a robot that navigates the file autonomously, reacts to the sign and the signals, and discovers gratefully with the condition of state change.
In conclusion, this project shows us how robotics, computer vision, and software engineering come together to solve real-world problems. Beyond building a robot that follows lines and reacts to traffic signs, we learned the importance of testing, debugging, and continuous improvement. This experience gave us valuable hands-on skills and demonstrated the potential of autonomous systems in everyday applications.